The prior example was a second-order regression. This time we're going to do a third-order regression. We're going to add just an additional order because we're going to estimate something different than before. We're going to estimate temperature 2 based on heater 1 changes. Now if you come here to the link, you'll see all of the source code and you can follow along here. And let me just walk through this. We have the two heaters right here that are next to each other. Now when we turn on heater 1, you see an immediate, almost first order response with TH1. Okay, so that one is going to have almost an immediate response like that. And then you see a little bit of a second order response in TC1, which is a sensor that's attached to the heater, but there's a little bit of heat conduction. It takes a little bit of time for it to go from the heater to the sensor. Time constant's about 15 to 20 seconds. And then we also have, right in between here, we have some natural convection and radiative heat transfer as well that transfers heat from one heater to the other one. Okay, so here is our second state, which is TH1. So we have our first one, this is going to heat up first. We have our second one, which is right here, and then we also have conduction to the sensor. Now TC2 is just going to be off. Okay, so that one is not going to be producing any heat. So everything that comes to TC2 is going to come from Q1, but it has to make a couple stops along the way. It comes here, and then the heat transfers here, and then finally down here. So each one of the stops, we're going to have those as lumped parameter models, and it's going to be a third order model. So if we just start with a physics-based model, we have TH1. This is an energy balance. We're going to have the convective heat transfer to the surroundings, a radiative heat transfer, and then also these two, which are convective heat transfer to heater number 2, back and forth, and the radiative heat transfer. And then this is our heat source term right here. Okay, this is our source for all of the heating. Okay, we're not going to have any Q2. Alright, then the next equation is just the balance equation for TH2. And then finally the conduction to TC2, which is the sensor. This is what we finally measure right here. Alright, so here's just some of those simplifying terms that you can add in. And here are the parameter values that we're going to use for this estimation. Okay, these are all the physics-based parameters, and we get those by estimating them from the data. So we do a sum of squared errors, and we fit the nonlinear model to the data. And if you come back to this site right here down below, you can just run this. It will help you collect the data if you have a TCLab, and then it will produce a plot for you. Okay, so I ran this earlier. I'll just click the get code, and let's just grab this, and I'll open up IDLE and select File, New File, and just paste this in here. Alright, and I'll put it on my desktop. Let's see if I can do that. Move it to desktop, and I'm just going to call this estimate. Alright, and then when I run it, if you don't have a data file there but it can connect to the TCLab, then it's going to run and generate this data for you. Okay, but I'm going to go ahead and close that because I don't want it to collect it. And if I just disconnect my TCLab, it's going to use the data from the internet, or if you let it run, it'll grab your data.csv file that you created. Okay, now I only created this small one right here. I was trying to estimate off of that. I'm just going to delete it, and then let's do it one more time. Alright, run it, and then it's hopefully come up with better better parameters here. Alright, so it just went and grabbed the data from the internet that I had collected previously, and you can certainly use that as well. But here's the second order model fit, or the third order model fit, sorry, from the physics-based model. Alright, so let's go on with developing based on these parameters that you just saw it produce. We're going to develop our own models here, and we're going to start with state space. So we're going to start with a state space model, and here we have our parameters. I'm going to just eliminate made a mistake here. This state should not exist right there, so I'll just eliminate that from the web page. But we have a 3x3 matrix right here, a 3x1 right here. We just need to find those parameters, and then we have a 1x3 and then a 1x1 right here. Okay, so this just says that TC2 equals TC2, and then that is 0 on the output term. Right here is my state space model right here, and we can come up with this state space model by evaluating the partial derivatives and then plugging in the nominal values right there. Okay, so this gives us a constant right here of this value, and then I would just plug it in my state space representation right up here. And then we're going to get our next one as well. Scroll back down. Alright, so here's my next one, and on down. Okay, just calculating the partial derivatives, plugging in the nominal values. That's going to give me coefficients, and then I'm going to have my A matrix. Alright, there's my A matrix of my state space model. Here's my B matrix, C and D. And now I'm ready to use one of these packages that can help me simulate this. I'm going to use one of two. This is one, the SciPy signal package. I can call state space and just plug in the A, B, C, and D, and then I can simulate it just with another line. And then I'll need to use the output Y. I can also plot the states if I want, and then I can plot that. Okay, here's the gecko. Okay, I created a new gecko model. I created a state space model with the A, B, C, and D. And then I'm going to shift this to iMode 7, which is sequential simulation, and then I'll solve it. So I can use either one of these to simulate the state space model to be able to compare it with the data. Now I also have a transfer function model, and the way in Python to get that with the SciPy signal package is you can just do the system that you had, the state space, and you could say 2tf, which is transfer function. Now it's going to give you something that's going to be not equal to 1 here. You can just divide the numerator and denominator by that to come up with this form, which is nice because that is our gain. That's going to be our KP, and then we have a third order system down below in the denominator. So I like to put it into this form. It's called time constant form. If you factor these into individual time constants, you could have tau 1s plus 1, and then you could have tau 2s plus 1, and then tau 3s plus 1. If you could factor that and get it into this form, it makes it nice because then you can see the time constants of each of the a time constant for each. There are going to be 3 time constants there. Alright, so and moving on, we can also use a time series model as well. So a time series model is just the summation of coefficient times the prior model values or measured values. So if you don't have any states here, this is going to be called an FIR, a finite impulse response model. Okay, and but we're going to use something called an ARX model. ARX is if you use measured values right here, or we can use something called an output error. Okay, so an output error is a little bit different, but right here we are going to use model predictions from the prior model predictions. We use those there instead of the measurements. Okay, so we have ARX and output error and finite impulse response. So we're going to do a 5th order. We're just going to estimate the 5th order parameters here. So we're going to have 5 A values and 5 B values that we're going to try to estimate. Alright, so let's go to our code, to the solution. We're going to import NumPy, Matplotlib, and Pandas, Gecko, time, and then also the SciPy signal package. We'll import the data. We'll try to read the local file first. If that one doesn't exist, we'll just go get it from the internet. Now, I know some Mac users, I saw the HTTPS didn't work there, so just take off the S. If the SSL is not secure socket library does not exist on your Mac in Python, then just take that off. Okay, so we're going to read the CSV, and then these are all the parameters that we just estimated. Now, yours might be a little bit different than mine, but that was from the first principles or the physics-based model estimation. I'm just plugging those in at the top so I don't have to run the script there. Here's my state space model with the A through D, and then I'm going to put a couple of these helper constants here that we saw from our state space model that we had done previously, and here are all the different coefficients. Again, Python is 0 based on the matrices or vectors, so you have to start with 0, 0 instead of A, 1, 1. Alright, there's my state space model with all of the non-zero coefficients filled in. And then we also have the state space simulation in Gecko. We use a state space function, plug in the U value, and then there's my time. I have my I mode 7, and then I'll solve it. Alright, here's a state space simulation with the SciPy signal package. It's signal.statespace. I have my T, Q, and then I'm going to be able to predict what the output is, Y. Now I'll print the linearized models. There's my state space model. Then my transfer function model, I'm going to use the to transfer function. I'll print that one as well. Then I have my time series model as well. So I have my state space, transfer function, and now my time series. Now this one, I'm just going to have my time, U, and Y, number of output coefficients, number of A values, number of B values, and then I'll print identifying time series model, and then use this function. There's some links there that I gave you in case you want to review how the package does that. Then I'll create a plot with each of these models with the data as well. There's my data. This one is my state space model, and then I'm also going to have my time series model, and the state space and the transfer function model, those are equivalent, so I don't need to plot the transfer function model. Okay, there's my Q1 value, and let's run this one. This is going to be solution.py, so let me just go find it in my files. I think I put it on my desktop. Alright, let's go back to desktop. There it is, and we will run it with IDLE. Okay, so first thing it's going to do is just get the data file if you have it. If not, it'll go out to the internet and just retrieve it. Okay, there's my state space model that was linearized, and then my transfer function model. Here you can see the numerator up top and then the denominator. Put the 1 right at the term multiplied by the s cubed, but you can just take it and divide everything by this value, which is make that 1 at the end, and then the numerator will be 0.28. So right now it's identifying the time series model, and then it will plot all of them together. So it has the data in blue, the state space is the purple dotted line, and then the time series, the 5th order model, you can see that's almost right on top of the blue. It's hard to distinguish the two. Okay, so the time series, the 5th order model, was the most accurate, but the linearized solution, that was fairly accurate as well. Probably good enough for controller development or other things that we want to do with the model later.